If we pump air into a balloon, we can see that multiple things are changing in that one balloon. Each of those quantities that change have a rate of change, and thus those rate of changes have to be related. This is the idea behind a related rates problem. We can ask questions about how one object is changing with respect to the other object that is also changing in the same scenario. So for example, if we know that a spherical balloon is being filled with air at a constant rate of 2 cubic centimeters per second, we can ask a question about how fast the radius is changing at a specific snapshot in time. For example, how fast is the radius increasing when the balloon has a radius of 3 centimeters? To answer a question like this, we'll go through 5 steps. The first step is draw a picture. Make sure that you understand completely the scenario that's being described. If we're looking at a spherical balloon and we're pumping it with air, we know that the balloon is getting larger, thus the radius is getting larger. There are other quantities that are changing too, but really they don't apply to this problem, so we can leave them out. But I'll mention that clearly surface area is changing as the balloon gets bigger. The cross-section circumference is changing as the balloon gets bigger. If the radius is changing, the diameter is also getting bigger. So there's lots of quantities that are changing. But this question specifically talks about volume and the radius. So I'll draw a picture that shows 3 stages of this situation that's happening, and then I'll label the quantities that are changing, specifically the quantities that are mentioned in the wording of the problem. After that, I want to assign symbols to each of the quantities that are changing. And typically we will use letters for our symbol, but we'll use letters in function notation. For example, I know that the radius of the balloon changes with time, so I will use r of t to write that the radius is a function of time. I also know that the volume of the balloon is changing with time, so I'll write v of t to say that the volume of the balloon is changing with time. Each of those quantities changes with time, meaning they have to have some rate of change. The derivative of the function r of t will give us the radius rate of change. The derivative of the function v of t will give us the volume rate of change. So for me, this is step 1. Draw a picture, typically 3 snapshots of what's changing, so that I can really see what objects are changing in my pictures, and then assign letters or symbols to each of those quantities and identify the symbols that we'll use for the rates of change. Next, step 2 is to identify the given information and the requested information. We are given that the air is being pumped into the balloon at a rate of 2 cubic centimeters per second. That is a volume, which means that's a dV dt. That's our rate of change for the volume of the balloon. And we're asked how fast the radius is increasing. We're looking for dr dt, and we're asking at the specific moment in time when it hits a radius of 3 centimeters. 1 second longer and the radius is no longer 3 centimeters. So we want that instantaneous rate of change when the radius is 3. That's my second step. Identify the given information and identify what we're looking for. The third step is to find one equation that relates the 2 quantities that are changing. In this case, we're relating radius and volume, and luckily there's a geometric formula that we can use. The volume of the sphere, it's 4/3 pi times the radius of the sphere cubed. That's one equation with both r and v inside of it. In some cases, that step can be a little bit harder, where you have to build the equation to relate the quantities that are changing. In this case, it's pretty straightforward. Once we find that one equation that involves the 2 changing quantities, we want to apply implicit differentiation. V and r both change with respect to time, so I'm going to differentiate the entire equation with respect to time using implicit differentiation. So I will get dv dt is equal to 4/3 pi times 3r squared times dr dt. We started with an equation that related the two changing quantities, and we turned it into an equation that relates the two rates. This is why it's called a related rates problem. We've got an equation that relates the change of volume to the change in the radius. Now we're ready to move on to step 5, which is plug in the given information and solve for the quantity that you're looking for. We are told that dv dt is 2 cubic centimeters per second, and we're asked to find dr dt when the radius is 3 centimeters. So I will plug in 2 cubic centimeters for dv dt, and I'll plug in 3 centimeters for r, and then I will simplify everything to solve for dr dt. Before I plug in any of those known values, though, it's worth simplifying if possible. I see 2 3's that could divide off, so we should do that before we plug in our known quantities. Plugging in our known quantities, we can simplify and begin to solve. So we want to isolate dr dt. I'll square my 3 centimeters on the right-hand side, multiply that to 4 pi. So now my equation looks like 2 cubic centimeters per second equals 36 pi centimeters squared times dr dt. Some people like to leave out their units. I like to include them because I want to do a bit of a unit analysis to make sure that my result sounds reasonable. We're looking for dr dt, which is the rate of change of a radius. And a radius is a linear measure. It's not an area, it's not a volume, it's linear. So my rate of change should be something like centimeters per second. And if I plugged something in incorrectly, maybe I noticed that I made a mistake because I didn't get a result that is centimeters per second. So I'll plug my units in and make sure that they reduce the way that they should to get the rate that I know I'm supposed to have. So I've plugged everything in. Now we're ready to divide the entire equation by 36 pi centimeters squared. That will give us the value for dr dt. And notice that we have centimeters cubed per second on top. We have centimeters squared in the denominator. Those centimeter units are going to reduce, leaving centimeter per second. Also, the 2 and the 36 will reduce, leaving us with 1/18 pi centimeter per second. That is the rate of change for the radius, specifically at the moment in time when the radius is 3 centimeters. Related rates problems are word problems, and it's always best to answer a word problem with a complete answer, like a complete sentence, so let's go ahead and do that. When the balloon has a radius of 3 centimeters, the radius is growing at 1/18 pi centimeters per second. And let's be honest, most of us don't know what 1 divided by 18 pi looks like, so it's worth putting a decimal approximation so that we know it's about 2/100ths of a centimeter per second.